Hello everyone, this is Dhanlakshmi, Assistant Professor from Tripoli Department of RMD Engineering College. In this session, I would like to discuss about polar plot where our unit 3 of control systems, which is going to be our frequency response. So in that frequency response where we'll be learning about Bode plot, polar plot. Right? So open loop response plots and closed loop response plot. So in that the polar plot, Bode plot are all are meant for open loop response plots. So here in this session, I would like to discuss about polar plot. So we'll see how to plot, how to do the polar plot, and from that how to get the gain margin and phase margin from the polar plot. So for plotting, for doing this polar plot, we need polar graph sheet. So we all know that the polar graph sheet where it is consists of concentric circles with radial lines. So it requires a polar graph sheet. Therefore, polar graph sheet, we can do the polar plot, and after plotting, we can find the gain margin and phase margin of the system. So when you take the polar plot, it is a polar plot of a sinusoidal transfer function is a plot. It is between the magnitude versus the phase angle. Whereas in case of Bode plot, it is the frequency versus the magnitude and frequency versus the phase angle, phase plot. So in Bode plot, we'll be drawing two plots. One for the magnitude, other for the phase. But in case of polar plot, we're going to draw a single plot which is between the magnitude and the phase. So it is a plot between the magnitude versus the phase angle of on the polar coordinates we're going to draw. So here you can see that the polar graph sheet will be like this, where it consists of concentric circles with radial lines. So for drawing this polar, we need polar graph sheet, and we'll discuss a problem and how to draw the polar graph, and then polar plot, and then how to get the gain margin and phase margin. But before that, you can see that this is the hint where based on the type number of a system, we can identify where in which quadrant the system will start the polar plot, and based on the order of the system will end up at that particular quadrant. So here you can see that if it is a type 0 system, it will start at this point. If it is a type 1 system, if it is a type 0 system, it will start at this point. If it is a type 1 system, it will start at this quadrant. And if it is type 2 like this, and here it will start from, and for type 3, it will be starting from here. Same way for the order of the system, based on the order of the system, the polar plot will end in this way. So this is for first order system, the plot will end up here, and for the second order system, the plot will end up here, and for the third order it is like this, and for the fourth order it will end up here. So based on the type number and the order of the system, we can sketch the polar plot from where it will start and where it will end up. Once again. So we'll go to a problem and we'll see how to do the polar plot, how to sketch the polar plot, and from that how to determine the gain margin and phase margin. So here I've taken a problem. So an open loop transfer function is given, G of S is given, right? G of S is given for a unity feedback system. The open loop transfer function G of S is given, and we need to sketch the polar plot. So we have to draw the polar plot, and we have to find out the gain margin Kg. We have to find out the gain margin Kg, and then we have to find out the phase margin gamma. So therefore, first step, in order to draw the polar plot, first step is let me take the G of S, and in that G of expression, I have to find out G of j omega. That is, wherever I have S, I am going to substitute S as j omega. So in this expression, wherever we have S, we are going to replace all that S by j omega. And once we replace all that S by j omega, our expression of G of j omega will become like this. Right? Now again, so here you can see that after this, what we have to do is we can find the corner frequency, but here finding the corner frequency will not help us, will not give the guidance to where we have to choose the frequency, like as in Bode plot. In Bode plot, based on the corner frequency, we will be choosing omega L and omega H, the lowest frequency, highest frequency, and keeping those corner frequencies as the references. Then we will find out for the set of omega values, we will find out what is the magnitude and phase. But here it is no way related. But still then we can, if you want, we can find out the corner frequency of the system here. So we know the first corner frequency will be omega, that is reciprocal of the coefficient of the j term. So therefore, for the first term, it is 1 plus j omega. For this term, it is 1 by 1. So therefore, it is omega C2 is 1, and here it is 1 by 2. So therefore, the corner frequency is 0.5. After finding corner frequency, now what we have to do is we have to write the magnitude expression as well as the angle expression. For writing the magnitude expression, what we have to do, just take this g of j omega. From this g of j omega expression only, we are going to write what is our magnitude as well as the phase angle, right? So magnitude and phase angle. For writing the magnitude, we're just taking the modulus of it. We're going to find out the modulus of g of j omega. So for this, we are going to find out the modulus. We know that the modulus of 1 is 1. So in the numerator, we have 1. So the modulus of 1 is 1. And for this term, j omega term, the next term what we have is j omega term. And for this j omega term, when we take the modulus, it will become root of omega square. So root of omega square will become omega again. And similarly here for the next term, that is 1 plus j omega term. So you can write, if you take the modulus of 1 plus j omega term, it will become the square root of real part square plus imaginary square. So therefore root of 1 square plus omega square. Similarly for this term also I have to take the modulus. So if I take the modulus, it will become 1 plus, that is square root of 1 plus 2 square is 4 omega square. So for everything on the whole, I'm taking the square root. Right? So this is how you have to write the magnitude expression for the given g of j omega. Then we have to write the angle, right? We have to find out the angle of this transfer function, open loop transfer function g of j omega. That is for that what we have to do for finding transfer function. This is actually 1 by j of j omega term. So for 1 by j omega term, we know that the angle is 90. Since it's an integral term, the angle will be minus 90. If it is a derivative term, if the j omega term is in the numerator, then it will be plus 90. Since it is an integral term, 1 by j omega, so therefore the angle is going to be minus 90 degree for the first term, that is for 1 by j omega term. Now for the second term, that is 1 by 1 plus j omega, when 1 by 1 plus j omega, which is a first order term in denominator, right? This 1 plus j omega term is a first order term, and this first order term is in denominator. So again, therefore it will become minus, right? So minus, and for the first order term, we know that how to get the angle, a tan inverse of imaginary by real part, right? So therefore tan inverse of the imaginary part is omega and the real part is 1, so omega by 1. Is that clear? So here you can see that the imaginary is omega, real part is 1. So the tan inverse of imaginary by real. Similarly, for this term, again, we have to find out the angle, since that is again a first order term in denominator. So minus tan inverse of imaginary by real. Right. So imaginary term here is 2 omega. So 2 omega divided by 1. So this is how we have to write the angle expression from the g of j omega. So once we write both magnitude as well as the angle expression, now we have to find out the ranges for different values of omega. What will be my magnitude value and my phase angle? So once again, you can see that for keeping this expression, in this expression for different values. So in this expression, once again, so in this expression, once again. So in this expression, right? So in this expression for different values of omega, we are going to find out what are all the magnitudes and phase angle, right? So therefore, that is what written here. So for different values of omega, I've taken the omega values 0.35, 0.4, 0.45, 0.5, 0.6, 0.7, and 1. So here you can see that for these different values of omega, these are the magnitude values we got, and these are the phase angle values we got. So we can substitute omega as 0.35 in that expression. We can find out what is the magnitude. Same way we can find out what is the angle. So so we have to complete this tabular column for finding the omega, for finding magnitude and phase angle for different values of omega. Right, after finding these values, now we have to plot it in the graph. So here you can see that the first value, the first reading what I got is for the magnitude of 2.2, the angle is minus 144. So just keep this alone. I'll tell you for this point, the same way we have to plot it for the remaining point. So let me tell you for the first point alone. So the remaining point is similar to that. So for the first point, you can see once again. So here the first point is for 2.2 magnitude, the angle is minus 144. Yes. So here you can see, let me go to the graph. Let me go to the graph here. So here you can see that, yes. Here you can see, yes. So here you can see that for the magnitude 2.2, see here the scale they have taken is, this is 0.5, this is 1, This is 1.5. This circle is 1.5 and this circle is 2, and here this circle is 2.5, right? So you can see that this 2.2 will be somewhere here. That is 2.1, 2.2, the fourth circle, right? So you can see that 2.1 and this is 2.2, the fourth circle. So this circle, you can see that the 2.2 and minus 144. So this is actually the minus 90, minus 100, minus 110, minus 120, minus 130, and this is minus 140. So here it will be minus 150, right? So minus 140, here is this line. This line is minus 140. So therefore 144 is the fourth line. So the fourth line and magnitude of 2.2 will come here, right? So this is the point where you have 2.2 and minus 144. Similarly, like this, what we have to do, we have to plot all the points here. So we have to plot all the points here like this. So that we have to complete this. We have to complete this entire tabular column. So likewise, we have to plot minus 150 for the magnitude 1.8, right? So same way we have to plot the 1.8 for the magnitude of 1.8, we have to plot minus 150. Like this, we have to plot all the points here. After plotting all the points here, what we have to do is we have to join all the points with a free hand so that we are getting a curve like this, right? So this is actually our polar graph, right? Polar curve, right? So polar curve, what we have to do after marking all the points, just join all the points with a free hand so that we will get the polar curve. Once we got the polar curve, now in order to find the gain margin and phase margin, what we have to do is we have to draw a unity circle. Unity circle is a circle which is having a radius of 1, right? That is what we call it as unity circle. So what we have to do, we have to just bold this unity circle, the circle which is having a magnitude of 1 or the radius of 1, right? So you can see that this is a circle which is having a radius of 1. So what we have to do, we are going to draw a unity circle. Once you draw the unity circle, you can check that the curve with the curve where it is going to cut the unity circle. So this is the point where the curve is meeting the unity circle, or it will cut the unity circle. That respective angle, right? So that respective angle you can mark it here. That respective angle you can mark it. That respective angle you can mark it here. So that respective angle you can see that. So you have to check where that unity circle and the polar curve, the point of intersection between the unity circle and the polar curve, the curve whatever you have drawn already, and the unity circle you have drawn now, right? You have to check the point where the unity circle and the polar curve is meeting together, right? Or it is a point of intersection. That respective angle, you can see that that respective angle will be. So here you can see that it is around somewhere here. So you can see here, right? That respective angle will be your 5GC, right? So that respective angle will be your 5GC. So we are getting this 5GC to be minus 166 or 168, right? So once we got this 5GC, now you can calculate your phase margin, where phase margin gamma is equals to 180 plus 5GC. So that is the formula for getting phase margin gamma. So phase margin gamma is equals to 180 plus 5GC. Here we are getting this 5GC as 166, minus 166. Right, so minus 166. So we have to substitute here. So 180 minus 166 will be 14 degree. Right, so 14 degree is our phase margin gamma. So this is how you have to get the phase margin. So for finding the phase margin, what you have to do, after plotting the polar curve, we have to draw the unity circle, and we have to check where the polar curve is cutting that unity circle or meeting or a point crossing that unity circle. That respective angle, right? That respective angle is our 5GC. Once we know the 5GC, gamma is equals to 180 plus 5GC. So therefore, if you substitute that 5GC, 180 plus 5GC, you will get that gamma, that is phase margin. Similarly, for finding the gain margin, you have to check, you have to bold the 180 degree line. So here you can see that plus 180 as well as the minus 180 line. So what you have to do, you have to just draw the 180 line and just see where that curve is cutting your 180 line. That is where that curve is meeting or crossing that 180 degree line. So here you can see that our polar curve is crossing 180-degree line at this point, and this magnitude, right, from origin to that magnitude is what called as g of j omega pc, right, g of j omega pc, which is around 0.7, right, which is around 0.7 here for this problem. So what we have to do, we have to draw the 180-degree line, and we have to check where that curve is going to meet that 180-degree line. That point of intersection, from origin to that point of intersection, the magnitude is g of j omega pc, and that value, reciprocal of that value, will give you the gain margin kg. So kg gain margin is equals to reciprocal of g of j omega pc, where g of j omega pc here is, it is 0.7. So 1 by 0.7 will give you the gain margin kg. Is that clear? So to get the gain margin, we have to draw 180-degree line, and we have to check where that curve is meeting that 180-degree line, and from origin to that particular point, the gain is going to be g of j omega pc. So reciprocal of that g of j omega pc will be our gain margin. And for finding phase margin, what we have to do, we have to draw the unity circle, and we have to check where that curve is meeting that unity circle, and that respective angle is going to be phi gc. So gamma is equals to 180 plus phi gc. Substituting there, we will get the phase margin. Okay. Thank you all.